Hello mathematicians, physicists, and engineers, and welcome to part 3 of this series on the Laplace transform. In this lesson, we're going to be working with the Laplace inverse. So it's going to be the second part of lesson 2. In lesson 2, we applied the Laplace transform to the differential equation, solve the algebraic equation. And now we're going to learn how to take that algebraic equation and apply the Laplace inverse. What we're going to do following this lesson is put all of this together to finally fully solve that differential equation. So as I said, I like to take this in parts so we really understand each component of the solution. Now, as we continue forward with this lesson, kind of want to give you an overview of what we're going to cover. I'm going to be using some examples covering partial fraction decomposition. And I'm also going to do an interesting example on completing the square. So let's go ahead and get started here. All right, let's start off here with our first problem. It's going to say find the inverse Laplace transform of the following functions. In part A of this example, we're going to be given the solution of the algebraic equation. So it'll say capital Y of S equals 7 over S plus 2 cubed. Now the goal is to use the Laplace transform table and actually invert this. The tricky part of this lesson is we always have to have these algebraic solutions in a nice format so it fits that table. So first things first, let's go ahead and apply the Laplace inverse to both sides. Now, as I said, we have to try to match up the form of this function here, of this function of S, to the Laplace transform table to be able to take the inverse. So if we look at the Laplace transform table, I see that I'm in a form similar to n factorial over s minus a to the n plus 1 power. Now I just need to figure out what is n. And if we look on the bottom, I have a cubed. So I'm going to take n to be 2 because 2 plus 1 would be 3. Now with that, I'm going to need a 2 factorial in that numerator where I have a 7. Well, the Laplace inverse is also a linear operator. So here's what we're going to do to solve this problem. I'm going to go ahead and pull out the 7 out of the Laplace inverse. And I'm going to just go ahead and put that 2 factorial in its place. I'm going to just put it up at the top of the numerator. Notice in the bottom, the exponent became 2 plus 1. I'm emphasizing that my n value is 2, and I am matching it to this table. Now, the problem is I just added in a 2 factorial. I cannot do that. I have to cancel it out. So on the outside, I made sure to divide by a 2 factorial to keep this equation balanced. So I added in the 2 factorial because I need it to use the formula, but I also made sure to cancel it out. Now, that being said, okay, let's just go ahead and apply this formula. 2 factorial will be 2, so that constant is going to be 7 over 2. Now, if we look over here, this is t to the n power on the left-hand side. So t to the n power e to the at. Well, n is going to be 2, so I'm going to have 7 over 2 t squared. That's where the t squared comes from in the answer. And then my a value is going to come from s minus a in the parentheses. Now, I have s plus 2 in the parentheses, so my a there is going to be negative 2. So the final answer is supposed to have e to the at, and my a is negative 2, so the final answer is going to include e to the negative 2t. We're now going to get into some examples using partial fraction decomposition. And partial fraction decomposition likes to show up a lot in the Laplace transform problems. So let's go ahead and get some practice with those now. And this part B is going to say capital Y of S equals S over S squared minus S minus 2. So how do we do this solution? Well, we're going to look at the denominator there, and we're going to go ahead and factor it. So Y of S is now going to be S over S minus 2 times S plus 1. And this is going to lead to the partial fraction decomposition. So we're going to go ahead and split this, and Y of S is going to be written as A over S minus 2 plus B over S plus 1. So we have two linear terms in my denominator, and the goal is to figure out these constants A and B to decompose this fraction. Now, what I'm going to do here is I'm going to take the decomposition and I'm going to set it equal to the original fraction. And that's what I have here. There are several tricks to finding partial fraction decomposition. I'm going to run through one here. So what I'm first going to do is I'm going to use the least common denominator here. And I'm going to go ahead and multiply the s minus 2 up there. So I'm going to take this s minus 2, and I'm going to multiply it up here to the b. I'm going to take this s plus 1, and I'm going to multiply it up here with a. Now that's going to give me a times s plus 1 plus b times s minus 2. And we always set it equal to the numerator of the original fraction. The numerator is just s. And now, as I mentioned, from here, there are several different techniques to figure out a and b. One of the quickest ones when it's in this form is to plug in certain values of s to essentially cancel out one of these terms. So what I mean is, let's first look at when s equals -1. So I'm going to go through this whole equation here, and wherever I see a s, I'm just going to plug in a -1. Why am I doing that? Well, I have a times s plus 1. If I plug in a -1 there, I'm going to get rid of the a term, and I'll be able to solve for b here. So let me just illustrate this. So I plug in -1 everywhere that's indicated. We do see that the a is going to disappear, -1 plus 1. And for my b term, that's going to leave me with -3b. And on the right-hand side, that is equal -1. So dividing both sides by -3, I do get my decomposition value for b, and that's going to be 1/3. Now, let's just go ahead and look at this equation again, but instead of choosing -1, we're now going to let s equal 2. And the purpose of that is to get rid of the b term and now solve for a. So as we did before, I'm going to go down the line and just plug in 2 at each step. So here I go ahead and illustrate that. I have a, 2 plus 1. And then again, look at the 2 minus 2 will cancel out the b. And on the right-hand side, I made sure to plug that in as well. So if I clean this up, I have 3a equals 2. Solving for a, I get a equals 2/3. And now I want to say, recall that b was 1/3. Why am I emphasizing these? Well, the whole point was to decompose the original algebraic solution. I know my a value and I know my b value, so I can just plug them in. I could put 2/3 and 1/3 in the numerator, but what I like to do is I like to pull them out in front of those fractions. So I'm going to go 2/3 times 1 over s minus 2 plus 1/3 times 1 over s plus 1. And the reason being is I'm always trying to get this in a form that easily matches the Laplace transform table. All right. So what we're going to do is now take the Laplace inverse of the previous function. So here's our decomposition, the 2/3, 1 over s minus 2 plus 1/3, 1 over s plus 1. Again, using linearity, I'm going to just go ahead and pull out the 2/3 first and apply the Laplace inverse to 1 over s minus 2. I'm going to then pull out that 1/3 and I'm going to apply the Laplace inverse to 1 over s plus 1. Now I'm going to go ahead and refer to the Laplace inverse table, and I'm noticing that the 1 over s minus 2 and the 1 over s plus 1 are fitting the exponential form here. So if I look on the right, I have 1 over s minus a, and I'm trying to invert it to give me a function on the left. So I'm trying to return a function of t. So I'm going to be returning an exponential function here. I just have to figure out what my a value is. Well, for this first term, a is just going to be 2. And on the second term over here, a is going to be -1. So here's how this final answer is going to run. I'm going to have 2/3, and the 1 over s minus 2, that's going to be inverted back to e to the 2t. So it's going to be e to the at, but a here is 2. Then I'm going to go plus 1/3, and that 1 over s plus 1 is going to be inverted back to e to the -t. Why? I have e to the at, but my a value here is -1. All right, let's look at an example now that has a quadratic involved in the partial fraction decomposition. So part C is going to say capital Y of s will equal s squared minus 4s plus 2. And this is all going to be over s times s squared plus 4. So we're going to decompose this fraction. And I'm going to have a linear term, and I'm going to also have a quadratic term. So for that linear term, I just put a constant over it. So I'll have y of s equals a over s. And that's going to be for the linear term. But the quadratic term, the s squared plus 4, in that numerator, I have to put bs plus c. All right, so I have to figure out now the constants, the 3 constants, a, b, and c. And once more, I'm going to take the a over s plus bs plus c over s squared plus 4 and set that equal to the original fraction. As we did in the previous example, I'm going to take this s and multiply it up here. I'm going to take this s squared plus 4 and I will multiply that up there. Once I do this, I'll have a times s squared plus 4 plus s times bs plus c. And I'm going to set it equal to the numerator of the original fraction. And that numerator was s squared minus 4s plus 2. Now I'm going to try a different technique here, and I'm going to compare coefficients to figure out a, b, and c. So what I'm going to do is I'm going to just go ahead and distribute that a. So in that first term, I'll have as squared plus 4a. And in the second term, I'm going to distribute the s. So I'll have bs squared plus cs. And again, it's going to equal the original numerator, s squared minus 4s plus 2. And I'm going to compare the coefficients. So what I mean is I'm going to compare the numbers in front of s squared, in front of s, and then I'm going to compare my constants. In order to do that, I want to gather my like terms. So I want to gather my s squareds together. So notice that I have as squared plus bs squared. I'm going to gather those two terms and factor out the s squared. And that's how I got this first term in this next step. So I have a plus bs squared. I put cs next, plus my constant now 4a, and again equal to the original numerator, s squared minus 4s plus 2. And I now want to begin comparing coefficients. I'm going to start with the s squared. So in front of s squared, I have a plus b. And that's going to be compared to the coefficient in front of this s squared. This equation has to balance, so that would mean a plus b would have to equal 1, the constant in front of s squared. And now I will compare the constant in front of s. So c would have to equal this constant here. C would have to equal negative 4. And then the last constant, 4a, would have to equal 2. Putting this all together is going to give me a system of equations here. So like we said, comparing the coefficients in purple, a plus b would have to equal 1. C there would have to equal negative 4. We actually already got a value for c. And then the gray comparison, the 4a equals 2, will allow me to solve for a. Let's go ahead and work on the system over here. So here's the system again. I have c emphasized because it's already solved for. I already have the value of negative 4, which is pretty cool. All right, let's go ahead and work on this. From the last equation, I can easily see that a would be 1/2. And if I plug that into the first equation, that's going to give me a quick answer for b to also be 1/2. So I have all my coefficients, and I can therefore decompose this fraction. Let's go ahead and look at the original state. I needed to figure out a, b, and c to plug in. And now I do have these numbers. And in the previous example, I tried to pull them out front. The reason being in the second term that I'm going to plug them in is I really don't know what that is going to match up to yet on the Laplace transform table. So I'm just going to plug them in on the second term. But notice on the first term, I did pull out the 1/2. So a was 1/2. I wrote 1/2 times 1 over s plus b I literally plugged in. I plugged in the 1/2 s plus negative 4 in the numerator for c. I left that all over s squared plus 4. And now I'm going to try to play around with this form to see where it matches up on the Laplace transform table. Now before I do that, I'm going to go ahead and split the second term. I'm going to split that into two fractions as so. So notice the first term stayed. I have my 1/2 1 over s. But I now took the 1/2 s and I put that as its own fraction as 1/2 s over s squared plus 4. And then I took that negative 4 and I also put that with the denominator of s squared plus 4. The reason being is when I have it in this form and take the Laplace inverse, it's going to match up nicer with the Laplace transform table. So here's the Laplace inverse applied. And now I'm going to start to compare this to the Laplace transform table. So let's see what we have. Well, this 1 over s is going to match up nicely with this first entry right here. So that's just going to return a 1, which is pretty cool. And now if I look at this term, it's going to match up pretty nicely right here to the cosine, right? And my last term here is going to match up pretty nicely to sine. And I say pretty nicely because it's not really exact. What's the problem? Well, notice that the a here has to be the same. And look at what we have. We have 4 and 4. So if I was going to use the sine Laplace inverse, that bottom 4 would be 2 squared. So the numerator would have to be a 2, not a 4. So we just have to make a little quick adjustment in order to get it in the exact form to apply the Laplace inverse. Let's go ahead and do that now. So how's that going to be done? Well, in the first term, I just go ahead and pull out the 1/2, and I'll have Laplace inverse of 1 over s. The second term, I go ahead and pull out the 1/2, and then I'll have Laplace inverse of s over s squared plus 4. Now, look at the last term. Here's where I did a little bit of manipulation. I said that I had 2 squared, so I needed a 2 on top, okay? Now, what I did is the original 4, technically 4 is 2 times 2, so I split it. I left the 2 in the numerator, and I pulled a 2 on the outside. So my 4 matches exactly to the Laplace transform table. I'm really set up now to just really go ahead and apply the Laplace inverse piece by piece. So let's go ahead and do that. The first one is going to be 1/2, and the Laplace inverse of 1 over s is just 1. So 1/2 times 1, it gives me 1/2 in my answer here in the green box. If we go to the second term, the 1/2 is going to stay s over s squared plus 4. Well, we said over here in the blue that is the cosine function. Notice that 4 is 2 squared, so that's my a value. A would be 2. So I'm looking at cosine of 2t in the answer, and that's where the 1/2 cosine of 2t came from. And then if I look at the final term, I leave the minus 2 out there because I had to fit the form exactly. And I have 2 over s squared plus 4. That's going to match the green circle here for the sine inverse. All right. Now that right there, my a value would have been 2. So I have sine of 2t. Let's go ahead and finish this lesson off doing an example with completing the square. So this example that I'm going to work with here is going to be y of s equals 2s minus 1 all over s squared minus 2s plus 11. Now notice the bottom is not going to factor, and if it's not going to factor, my solution is going to be completing the square. So how is it that I'm going to complete the square? Well, we always look at the b term of a quadratic, so here it would be -2. So -2 divided by 2 would be -1. I square that, it gives me an answer of 1. So I'm going to add and subtract 1 to my denominator, and that's what I have emphasized here. Now, why do I add and subtract 1? Well, the technique of completing the square gives me a nice factorable form. Those first 3 terms in the denominator, the s squared minus 2s plus 1, that's going to factor very nicely to s minus 1 squared. And then I go over here and just clean up a little bit. -1 plus 11 will give me plus 10. All right. Now, if I go and reference the Laplace transform table, I'm in a form that's pretty similar to one of these two. It's going to be an exponential times sine, or it's going to be an exponential times cosine. I just got to do a little bit of manipulation. Now, if we look at the cosine one, notice that it has s minus a in the denominator and s minus a in the top, meaning it has to match exactly. But in our fraction, we have s minus 1 squared in the denominator, but we have 2s minus 1 up top. I would need s minus 1 exactly in order to apply this cosine formula right from the table. So we're going to do a little bit of manipulation to try to get that to work. I really want the s minus 1 in the denominator to match the s minus 1 up top. So the first problem I have is that 2s, okay? I'm going to go ahead and factor 2 out of the numerator. That way I just have s instead of 2s. Because notice over here on the formula, it's s minus a over s minus a squared plus b squared. So if I factor out the 2, my numerator will become s minus 1/2. The denominator stays the same as s minus 1 squared plus 10. Okay? What I'm going to do here is essentially try to force my s minus 1 in. It's a common trick that's done in Laplace transform problems here. So I'm going to force the s minus 1 in, but I'm also going to add 1. So what I did is I really just added 0 in there to make it work. But notice I do have my s minus 1. I'm going to clean this up just a little bit here. So I'm going to have 2, and then I'll have my s minus 1. That 1 minus 1/2 will leave me a positive 1/2 on top. My denominator is going to stay the same as s minus 1 squared plus 10. So notice that it's starting to match up a little bit better to this Laplace transform table. And let's go ahead and keep working with it over here. Again, I'm going to emphasize that I was really trying to get this s minus 1 to match up in here. And then I do have it in here at this phase. And I'm going to go ahead and split this now into 2 separate terms. So I'm going to split that fraction. Again, I'm going to leave the 2 on the outside of these parentheses. And that first fraction is going to be s minus 1 over s minus 1 squared plus 10. Then I'm going to go plus 1/2 all over s minus 1 squared plus 10. So splitting this fraction here. And now I'm going to go ahead and just distribute the 2 to both of these fractions. So if I take the 2 into the first one, I'm still going to leave the parentheses. It'll be 2 times s minus 1 all over s minus 1 squared plus 10. And then when I distribute the 2 into the second fraction, the 2 and the 1/2 will turn to a 1. So I have 2 nice forms here that'll start to line up pretty nicely with the Laplace transform table. All right, so since I'm in a good setup, let's just go ahead and apply the Laplace inverse now. And I'll go ahead and handle this term by term. So I'm going to apply it term by term. In the first term, the 2 is going to pull out, and I'll have Laplace inverse of s minus 1 all over s minus 1 squared plus 10. And the second term, I'll have Laplace inverse of 1 over s minus 1 squared plus 10. And now I'm going to be comparing both of these terms to the Laplace transform table. So here's our setup from our previous calculations, and here's our Laplace transform table. So let's go ahead and match it up the best we can. Notice that this first term now is going to line up pretty nicely with the exponential times a cosine setup, especially since we have s minus 1 in the denominator and numerator. Matches nice now after that manipulation. This second term right here is going to match up really nicely with an exponential times sine. Well, why is that? The numerator there is just a constant value b, which is what we have, and then we have a s minus a squared term plus some b squared term, which we'll actually make that happen in a moment. But we see that we're in good shape to start applying this table. We got to do a little bit of manipulation on the blue circle, but that's fine. Let's go ahead and try this out. What is it that we're going to do? All right, let's look at our first term here. The 2 is going to stay. And I'm doing the Laplace inverse, and notice what happened. In the orange circle, I had s minus 1 over s minus 1 squared plus 10. But now in the first term, in the next step, I have s minus 1 all over s minus 1 squared plus the square root of 10 squared. So I'm emphasizing this right here. Well, the formula for cosine over here in the orange circle, it says plus b squared. My b value here would be square root of 10, okay? So that's good to know because I'm doing cosine of b. I would have cosine of square root of 10t when I'm done. So that takes care of that first term. But now for the sine, the blue circle, the 1 over s minus 1 squared plus 10, I got to do a little bit of work. The reason being, the b is supposed to match. B is square root of 10, okay? But I do not have that in the numerator. I have a 1. It has to match. So I have to make it happen. I have to make it match. So I go ahead and put a square root of 10 there, but I just can't place any number I want. So on the outside of the Laplace inverse, I go ahead and divide by square root of 10, or I multiply by 1 over square root of 10. So I forced the square root of 10 in, but I also canceled it out on the outside of the Laplace inverse. And now all of this is a nice setup to just go ahead and apply the table. So let's do this piece by piece. That first term. So I have 2. And the first term is now e to the t cosine square root of 10t. Why is that? Well, I have s minus 1 squared. If we look at the cosine formula over here in the Laplace transform table, it's s minus a. My a value there would be 1, and it inverts back to e to the at. So this would be e to the 1t, or just e to the t. And we already mentioned that the b value, which is that orange arrow, would be square root of 10. So it's going to be cosine of bt or cosine of square root of 10t. So you're just plugging it into the formula on the left-hand side of this table. If I go over here to the second term, I go plus 1 over square root of 10. That constant is just going to come down. The e value is going to be the same. This is still e to the at. A there would be 1 because it's s minus 1 squared. And now this is the sine formula. B is still going to be given by these blue arrows, and b is the square root of 10. So I'll have sine of square root of 10t.